Namaskara. We will continue our discussions about inverted tree forest based implementation for the minimum spanning tree algorithm by Kruskal. Okay. What we have seen is the following. The find operation takes time proportional to the height of the tree. That is because it is done by ancestor chasing. Okay. Union on the other hand is done by, its order 1, it is done by tree hooking. Okay. In order to get an idea about the worst case complexity of find operation, consider the trees that may get generated through a series of union operations, because union operations only hook the trees and create bigger trees. We are starting with the isolated vertices, right. All these trees are of height 0, there are no edges. But as and when you hook trees, things could become taller and taller. You may get bigger and bigger trees. So consider the following, let us say this is 1, 2 and this is n. Consider union operation n minus 1 n. When you do the union operation n minus 1, the smaller one will be put in the top, the bigger one will be hooked to it. So you will have n minus 1 and n will be hooked to it. Other things will still be isolated vertices. Then let us say you are performing union n minus 2 n minus 1. So this is going to hook n minus 1 to n minus 2. So n minus 2 may be an isolated vertex. Now n minus 1 will be hooked to it after this, because that is smaller, this one is larger, and so you are going to have this tree getting hooked to it. And again if you perform union n minus 3 n minus 2 to n minus 3, this tree will get hooked. At n minus 3 there will be a self loop, this will not be there anymore. Okay. So now you can see finally union, let us say 2 1. This is going to create, when you do all these unions, you are going to have at 1 a self loop, 2 getting hooked to it, 3 getting, and so on, and finally n connecting to it. It is a very tall tree, the height of the tree is n minus 1, it is order n. There are n minus 1 edges from 1 to n all the way. It is a long chain. Okay. So I have a series of union which results in a tree like this. It is a very tall tree. So the find operation in this case can take order n time, order n steps. The ancestor change, because there are long paths from the node, you may have to go all the way up, and therefore in this representation find, the complexity of find is order n. So let us contrast. We have two data structures studied so far. One is the name array and another is a parent array. union takes in name array order n time, in parent array order 1 time. Find takes in name array order 1 time, but in parent array it can take order n time. So, I have a new data structure which has a totally different property. You can see that the complexity figures are different. Suppose I use the parent array or inverted forest data structure to implement my Kruskals algorithm, right. I have a code and I want to implement my code using the inverted. So, if you go back and see the code, you will see that the code was performing 2m find operation and n minus 1 union operations. For each edge 2 find operations are done, and for each edge in the tree 1 union operation was done. Therefore, 2m find and n minus 1 union operations were performed by that algorithm. What will be the complexity? Now, each m find is n, therefore, this will be order n m, and n minus 1 union is order n. Okay. Therefore, this is n is way smaller than nm, you can lower order term can be ignored. Therefore, the complexity of the implementation of Kruskals algorithm using inverted forest will be order n m. This is the complexity using the parent array based implementation. So, we can compare and contrast. One algorithm is order m plus n square, another algorithm is order n m. So, a graph is said to be dense if there are a lot of edges. M can be as high as theta n square. There can be n square edges. If a graph is dense, you can see that this is n square plus n square is anyway order n square. Whereas this one n m, n times n square is n cube. Therefore, this is more like for dense graph m is order n square. In that case, name array has complexity order n square plus n square, which is order n square. Parent array or the inverted forest representation is order n times n square is, which is n cube. You can see that it is a bit inefficient for an order slower than our first solution. Okay. Our first solution is m plus n square, whereas this solution is nm, which could be which could go as high as n cube. All right. For sparse graph, that is if m is order n, both are same, n times n is n square, here also it is n square. For sparse graph, their performances are comparable, they are of same order. But for dense graph, the second one is more inefficient than the first one. Okay. This what we have got. So, let us write for sparse graph. Say m is of order n, right. Even n log n is considered sparse, but we are taking extreme for making our argument clear. This will be order n plus n square, which is order n square. This is order n times n, which is order n square. Both of them for sparse graph where m is order n, their performances are comparable, they are of same order. But for dense graph you see some difference. The second one is more inefficient. Is there a way in which we can improve the second one? Okay. It turns out that we can improve the second one in several ways. We are going to see two significant ways in which our second implementation can be improved. Okay. So, the inefficiency of the find comes into picture mainly due to the trees that are created during union operation. Union operation, by hooking the trees, are creating bigger trees. Can we make sure that it does not create very tall trees? In other words, is it possible to find a way to perform the union operation so that it does not create very tall trees? Okay. Can you do union in a careful manner so that no tall trees are ever created by whatever is the union that you do? Okay. You do not know which two sets you are going to combine at what stage of the algorithm. You are going to perform n minus 1 union operations. There are some sequence of n minus 1 union operations which may result in a very tall tree. Is there a way in which I can do the union in such a way that I never get tall trees? Or can I have a decent bound on the trees, the height of the trees created by the union operation? It turns out that we can achieve that in a very simple manner. Okay. So, here is the way in which you do the union operation. Okay. How to improve? The second implementation, that is the inverted forest based representation. How do we do that? Okay. The key idea is perform union operations in such a way that we never get a very tall tree. In other words, we should have some bound, a good control on the height of the tree that are generated. Okay. So, this we do by doing the tree hooking in the following way. Okay. The tree hooking is going to be done in the following way. Hook the smaller tree with larger tree. Therefore, here I drop the convention that the minimum should serve as the name. That is not necessary. The value at the root will serve as the name of the set. Value at the root will serve as the name of the set. Whatever is the value, it need not be minimum. Okay. Anyway, if they are in the same tree, the ancestor chasing will take you to the root. Whatever is the value, it will be same for both of them. So, we are checking whether they are same or different. Therefore, we will ignore the convention that we would like to have the minimum to serve the name. Any value which is at the root is going to act as the name of the set. Therefore, we are going to maintain another piece of information, namely the size, okay, and it is based on the size. A smaller tree will be hooked to larger tree. So, initially we will have this is done by P of I equal to I, and what is size of I? Size of I equal to 1 for all I, 1 less than or equal to I less than. Each tree has size 1, there is only one node. Therefore, the size of the tree is, and I is the root. So, there is a tree rooted at I and that tree has size 1. This is the initial configuration, and this is how the size array is introduced. Another bookkeeping information is added to our implementation. Now, the union operation is going to be done in the following way: union x y. What we are going to do is the following: if size of x is less than or equal to size of y, then we are going to hook the smaller tree with the larger tree. Then parent of x equal to y, smaller tree will be hooked to the larger tree. After hooking, x is not anymore the root of a tree, okay. Therefore, only y is the root. So, update only size of y. Size of y equal to size of y plus size of x, right, because they are disjoint sets. When you take a union, the cardinality adds up. The number of nodes is simply addition of okay. After this, well, you can do this or you can even ignore this, it does not matter. You can make size of x equal to 0. This is only optional, you do not have to do that. If you do not want, it is okay. You make size of x 0 to indicate that, well, there is x is not anymore a root, it is hooked and it has gone under some node. Currently it is not the name of any set, that is indicated by that, but you can simply ignore it, okay. So, if size of x is less than or equal to size of y, else parent of y equal to x, else y is hooked to x, and you have size of x updated to size of x plus size of y. If you want, optionally you can set now size of y equal to 0, or you can ignore this step, it does not matter. You can see that union is still order 1, union is still order 1, only one comparison is done and one assignment and one addition, it is still order 1. There are 3 you are doing only 3 operations instead of only 1, that is okay. So, union is still order 1. What kind of trees this is going to produce? What will be the heights of the trees that are produced by such a union? This kind of a union is called weighted merge. It is a tree hooking, but the hooking is done based on the weight or the size, okay. So, this is called weighted merge, union by weighted merge. When you perform union guided by the weight, this configuration is changed to this configuration. You have a self loop here and you have a self loop here. You will have only self loop here. This is x, y. Size of x is less than or equal to size of y. A small tree is hooked to larger tree. Okay? A smaller tree is hooked to larger tree. When you do like this, we are going to prove that you are never going to have a tree whose height is more than log n. In other words, any tree that is generated at any time during this union operation, when you do union like this, will always be less than or equal to log n. No tree will be having height more than log n. In other words, all trees encountered at any time will have height less than or equal to log n. So, cost of the find operation because of that is less than or equal to log n, upper bound by log n. So, how do you argue that you will never going to have a tall tree, or you are never going to have a tree with height more than log n? Okay? You are hooking a smaller tree with a larger tree. Whenever you do the hooking, right, the depth of a node, certain nodes will have their depth increased by 1, certain nodes will not get any increase by depth, right. So, consider this tree hooking done. Let us say Z is a node here. What was the picture earlier? The picture earlier was like this. Z was here. Let us say this is x. This is y. Earlier, from Z to the root, if you have to go, you will be going whatever is its depth, the depth of Z, let us say 10, then you will go 10 steps. But after this tree hooking, you have to go one more step, because this is where the root is now. So, in addition to this distance, you have to make one more step to reach the root, and you will give the answer. Okay? The complexity of find x performs depth of x steps. If x is 10 level below from the root, then in order to go up, you have to go through those 10 levels and reach the root. Find x performs depth x steps. Initially, depth of x is 0, because you had x in a self loop initially. Later on, x gets the tree containing x gets hooked. Okay, for example, consider Z. The tree containing Z is hooked, so Z has gone one more level deeper. Okay, but the same tree hook operation, if you take a u here, whatever is its depth, the same depth it will have even here, because for u the depth is not changed, but for z the depth has changed. So, some nodes have their depth increased, some nodes do not have their depth altered. Okay? So, fix an z, fix a vertex z. Look at its journey, look at the trees in which, let us look at the trees in which z is placed. Let us look at the trees containing z, let us look at the trees containing z at various points of execution. Let us consider all the trees containing z, because you may ask find z at any time. At the time of calling, whatever is its depth, that many operations you would perform. For example, find z will perform, let us say its depth is 10, it will perform 10 steps, but find z here will perform 11 steps. That is because z has gone deeper, z has gone one more level down. Therefore, its cost, the find operation for that is now more. Okay? So, fix an z and let us look at the trees in which z is placed, or the trees that are initially z was in a tree of size 1, in a tree of size 1. Now, after hooking, z will be of size greater than or equal to 2, because this is hooked to a tree of size greater than or equal to 1. The smaller one goes to the bigger one. When you put both of them, it will be in a tree which is greater than or equal to 2. Now, z has got one level down. Again, suppose this tree is hooked to something else, then z will be in a bigger tree and that tree size will be greater than or equal to 4, because you are going to merge the tree containing z with a larger tree. So, the next tree that is going to contain z will be greater than or equal to 4. Again, let us say this tree is merged to some other tree, that will be larger, that will have minimum 4 or more element. Together they will have greater than or equal to. So, in this way you can have only log n stages, because this is greater than or equal to 2 power k, you can have only n maximum, assuming all nodes are. So, this process can go on only k stages, where k is log n. Each stage z gains 1 unit of depth. Whenever z is moved from a smaller tree to a larger tree, whenever z moves from a smaller tree to a larger tree, its depth is increased by 1. Whenever z moves from a smaller tree to a larger tree, because tree hooking, you can see the picture here, z was earlier here and now z is in a larger tree and its depth is increased by 1. But this kind of a movement, every time when it moves, the size of the tree doubles, more than doubles. So, if you look into the trees containing Z, it keeps doubling. So, how many doublings can happen? Only log n doubling is possible. In other words, and so Z when Z moves from a smaller tree to a larger tree, the size of the tree, containing Z at least doubles, okay, greater than 2, because here you have Z, its size is k, this must be greater than or equal to k, and when you are k greater than or equal to k, so Z in a tree of size k, now Z is in a size greater than or equal to 2k. Therefore, for each increase in depth by 1 unit, okay, for each increase in depth of Z by 1 unit, the size of the tree containing Z at least doubles. All right. So, how many increase in depth possible? This implies there can be at most log n increase in depth for, it means there can be at most log n increase in depth for Z. You cannot increase more than this, because each increase doubles. How many increases are possible? From 1 to n, maximum log n. When you keep doubling, you can have only, so 1, 2, 4, there are only log n stages, log n doublings are possible. For each doubling, there is a gain of depth. Initial depth of Z is 0. Initial depth of Z is 0. That is because Z was in a singleton node initial, and this implies depth of Z is less than or equal to log n at any time. At any time, the depth of Z is less than or equal to log n. The maximum it can go is only log n. This is for an arbitrary Z. I have taken an arbitrary Z and I have argued that its depth is not more than log n. Okay? Since Z is arbitrary, whatever we have shown is true for, okay, all vertices. Since Z is arbitrary, since z is arbitrary, we conclude that depth of any node is less than or equal to log n at any time of the execution. Initially it may be 1, little later it may become 2, little later it could become 3, but at no time it will be more than log n. Various trees of various sizes will be there, but no tree will be a tall tree. That is because no node is more than log n distance away from the root. This implies, okay, cost of find operation, find z for all z is less than or equal to log n. Complexity of find is less than or equal to log n. So we have now 3 implementations: name array, parent array, same parent array with weighted union. So union is order n here, this is order 1, here is also order 1. There are more steps, but still order 1. Find is order 1 here, order n here, but order log n here. We have significantly reduced. So let us look into the complexity figure. What is the complexity if I use weighted merge based union, the same code, but now my union routine has a different implementation. It has got weighted union. The find is same, ancestor chasing, only the union code is altered. That results in this complexity. In Kruskal's algorithm, we have done 2 m find operations and n minus 1 union operations. These 2 m find operations will take 2 m log n. This n minus 1 unions will take, because each union is order 1, order n. This is the dominating term, therefore the complexity is going to be order m log n. Therefore the complexity is order n plus m log n, which is order m log n. You are ignoring the lower order terms. It's how m log n compares with n plus m square. You have m plus n square algorithm, you have m log n algorithm. Which one is better? Now for dense graph, m equal to n square, therefore this becomes n square plus n square, that is O n square. This becomes n square log n, which is O n square log n, some order log n more, okay. But for sparse graph, m is order n and this becomes n plus n square, which is order n square, because n square is a dominating term. But here it becomes order n log n, which is much better than n square, because m is n, m log n means n log n, okay. Therefore for sparse graph ours is better. The new data structure is better for sparse graph, but for dense graph the name array is better, because for dense graph this is n square and this is n square log n. But for sparse graph, this remains n square, whereas this has become n log n, which is a significant improvement. Okay. So, in some cases it is better, in some cases it is poor, okay. It is worse than that in some cases, it is better than that in some cases. It is a kind of a comparison. Okay. We can further improve this, it is possible to improve this further, and we will take a closer look at that improvement in our next discussion. And that is going to be a fairly significant and mathematically way too advanced. Okay. So, we will have a detailed discussion on the next improvement that we are going to bring in for our inverted forest based representation in our next discussion. Okay. But that is going to be way too mathematically, the analysis is very sophisticated and advanced, fits right in the intermediate or advanced level of discussions in the algorithms course. Okay. I stop at this point the discussion related to this. We will continue our discussions in our next session on further improvements for this scheme. Thank you.